Hello. Welcome to Basic Probability Ideas and Practical Applications. We're going to be going through the main ideas in probability, and it's much better than learning through a textbook. So probability is ubiquitous, and it's needed in several quantitative disciplines, ranging from quantitative finance to machine learning. And in this tutorial, I'm going to cover some basic ideas for probability and some practical examples. We always start off with a practical example with basically flipping a coin, right? It could either land heads or tails. So a sample space is something that all possible outcomes that can occur in a random experiment, right? And the definition of probability is the measure of the likelihood that that event will occur. So in the sample space here, heads and tails, it could either be heads or tails, obviously. And that would be considered a subset of the possible outcomes in the sample space. So the event of getting heads is obviously E equals heads. Now there's some basic probability axioms, which are you can interpret as laws. Okay, so the probability of an event A occurring between 0 and 1, okay, that's the probability of something occurring. It's going to be 0 to 1. Okay. The probability of the entire sample space of occurring, right? Either heads or tails, it's going to be 1. It's definitely going to happen. And then for any two mutually exclusive events, A and B, probability of A or B is going to equal to probability of A plus probability of B. Now, there are different types of events. There's an event that consists of a single outcome. Um, there's a compound event, which is an event that consists of more than one outcome. Mutually exclusive events, two events that cannot both occur at the same time. Example is a coin toss. Heads and tails are mutually exclusive, right? So you can't get heads and tails simultaneously in a coin toss. And then there are independent events, which there are two events that are independent. It doesn't affect the probability of the other. Okay, so flipping a coin twice, one after the other, the first flip is not going to affect the second flip. Now, for computing probability, you can see that there's the number of favorable outcomes divided by the number of total possible outcomes. So the probability of drawing an ace from a deck of cards, which consists of 52, is going to be 4 out of 52. There are also something called complementary events. The complement of an event A is the event that A does not occur, right? So PA to C is equal to 1 minus PA. Okay. So if the probability of raining tomorrow is 0.3, the probability that it won't rain is 0.7, 1 minus 0.3. The probability of rolling a dice, this is another classic example. We have a sample space of 1, 2, 3, 4, 5, 6. The probability of rolling a 4 is 1 out of 6. The probability of rolling an even number, 2, 4, and 6. We have three of those, so it's going to be 1/2. 3 divided by 6 is equal to 1/2. Now we're going to be talking about a random variables. A random variable x is a function that maps outcomes of a random process to real numbers. So you could see it as a function that basically translates a random occurrence into the real number line. So in discrete case, we would take countable values, right? Say the number of defaults in a stock portfolio or bond portfolio, or the number of calls in an hour at a call center, right? And they're all going to be integer values, okay? Continuous takes values in continuum. So it's like a stock returns, right? And we're going to see that in decimal places. So that's an easy way to remember what type of random variable we're dealing with. Now, if you simulate a dice roll and we do it like we make like 10,000 rolls, Excuse me for this. We could see that the outcomes are equally likely. Okay. And that makes sense. I mean, it's basically something called a uniform distribution, where the outcomes are equally likely. And we could test these kind of these theoretical ideas, like, you know, with actual simulations. Okay, so that's what we're doing here. Now, in the continuous case, it's basically a stock return. And you could see that basically we've got a normal distribution here, right? A normal distribution would be a continuous distribution. A uniform distribution would be a discrete distribution, right? So those are two examples that illustrate the ideas of a discrete and a continuous distribution. Now, moving on, we're going to go into some basic probability statements. And here we've got this DoorDash example. Say their DoorDash deliveries, about 1,000 of them between 5 minutes and an hour. Okay. So what we would do here is we basically simulate a uniform distribution, right? Where all of these between 5 minutes and 60 minutes is equally likely, right? And there's going to be 1,000 of them. Now, what if we wanted to capture the probability that the delivery time is between 10 minutes and 20 minutes here? What we would do is we would take delivery times is greater than 10 and then delivery times is less than 20. Okay. And we would get the probability of that. And it would be 0.19. If we wanted to know the probability that the delivery time is greater than 20 minutes, we would do this. NP dot mean delivery times is greater than or equal to 20. Okay. And then if we wanted to know that if it's less than or equal to 20 minutes, we would do this. Delivery times is less than or equal to 20. Okay. Here I'm just showing like basically if it's true or not, if the probability statements are true or not. But um, and that's what we're basically doing. We're trying to capture the probabilities of x is greater than or equal to 20. It would be true, true, true out of the 1,000, and then it's taking the mean value. Okay. Now, Amazon session times is another example we could work with. We want to know like how long a person is going to be on the website. It could be 3 minutes, 5 minutes, go up to 60 minutes, and everything in between. Okay, so if the probability that it's less than 20 minutes, we do NP mean, NP array, session times is less than 20. We get 0.6, probability of 0.6. Between 10 and 30 minutes, we get 0.4667. So now we're going to go on to talking about expected value. And there's a formula for the discrete case and the continuous case. The discrete case is a summation, and then basically the continuous case is an integral. Okay. We take integral of x times f of fxx, okay, which is the function. And then p of x is equal to x, okay? This function, this PDF, could be like a normal density. This could be something like along the lines of a uniform distribution. And in our classic dice roll case, basically, we see that x times p of x is equal to x is 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6, which is equal to 3.5. So that's the expected value of a dice roll. And obviously, we could express that using Python. You could see this kind of this list comprehension type for loop where we're multiplying x times the probability of each, right? So it'd be like 1/6 times 1, 1/6 times 2, and so forth. Stock returns are, as I mentioned earlier, it's going to be continuous. Okay. We simulate that from a random normal. I mean, I just basically took some arbitrary mean and sigma values. This is something that could be played around with, changed and experimented with. And we see that we just take the mean of the returns to get the expected value. Now, there's something called linearity of expectations. And it states that the expected value of the sum of the random variables is equal to the sum of their expected values. So this property holds regardless of whether the random variables are independent, meaning that it'll hold even though the random variables are dependent. Now you see this EX1 plus X2 is just taking EX1 plus EX2. And then we see that also the constants, if it's multiplied by a constant, we're going to take the constant outside of the expectation of those the random variable x1. So we see let x1 as an example, x2 represent the outcomes of a dice roll. We've got 3.5, right? They're both the same, right? Because they're independent. We add them up and the expected value based on the linearity of expectation is 7, okay? When we add two of these uh, fair dice rolls, okay? Here's an example of the scaling that I mentioned. Okay, so if now suppose we define y is equal to 5x, we would take this constant and put it outside of the expectation. We know the expectation is 3.5 from earlier. 5 times 3.5 is 17.5. So that's the expected value of y. Okay. So constants can be factored outside of the expectation, factored out. Okay. So here's an example with linearity holding even with dependence. So suppose you draw two cards from a standard 52 card deck without replacement. X1 is equal to 1 if the first card is a heart, else 0. X2 is equal to 1 if the second heart, else 0. So these are dependent random variables since there's no replacement. If you take a card that's a heart, you're going to replace that. You're not going to replace it. Okay. But the expected value, okay, is the average, right? It's not the actual draw. So expected value of x1 plus x2 is equal to 13 divided by 52 plus 13 divided by 52 is equal to 26 divided by 52 is equal to 0.5. Okay. It's on average what you're going to draw. So it's going to be 13 divided by 52, not 51. Okay. So there's a distinction between that, where you're taking the expected value of a draw and you're taking an actual draw. If you're taking the actual draw, yes, it'll be with replacement. Without replacement, it'll be 13 out of 51 on the second draw. But we're taking the average. That's why it's 13 out of 52. And I run a simulation on that basically, and I kind of show that um, we get an average of 0.494 for two cards. It's 0.5 out of about 10,000 trials. Now, moving on to variance and standard deviation. It's basically variance is measuring the spread around the mean, the variability around the mean. So you could see that E of EX, expected value of X, is obviously the mean. Hopefully people have caught on to that idea. And then we've got EX squared minus the mean squared, okay? Which is equal to variance. And the standard deviation is basically the square root of that. Now, going back to our dice example, we get obviously the expected value is 3.5. I mean, this one's a little bit slightly off, but it's forgivable, right? And then we compute the expected value of x squared, right? Which is outcomes times squared, because we're squaring each of these dice rolls, 1 to 6, and we're taking the mean of that. And then we take the expected value squared minus the expected value squared. Okay. I know that sounds a little strange, but you see this expression here. And we get these two, and then finally we get the variance, which is this relationship here. Now we're going to be moving on to joint probability. So the joint probability of two events A and B are denoted as probability of A, and this here is an intersection B, or probability of AB. Okay. It's a probability of events occurring at the same time. Okay. Probability that both A and B will occur. And then there's a conditional probability. Probability of A given B is equal to probability of A and B divided by probability of B. And this is the conditional. And it's used in Bayesian inference, risk modeling, and whatnot. Now, going back to our dice example, so what's the probability of calculating that the roll will end up being 5, given that x is greater than 3? Okay. Um, I'm trying to look for it, but I'm not able to find the scrolling thing. But how would we do that? So we would first have to look at this condition, x, anything that x is greater than or equal to 3, right? And we find that it's 4, 5, and 6, right? Now, what's the probability out of the 4, 5, and 6 that it's going to be a 5? It's going to be 1 out of 3. Okay. So that's what you're doing. What's the probability of something conditioned on another mathematical um, expression, which is x is greater than 3 in this point. And here we do the same thing. We could use a list comprehension to express this, the mathematical expression that I just discussed. X for x in outcomes if x is greater than 3. Okay, so those are the conditioned outcomes. But then we count the total number of outcomes under those conditions, which we can use a 5. And we get 0.33, right? The total, obviously, we're going to divide that by the favorable divided by the total, and we get the conditioned. Okay. Here's another example. I mean, this is pretty straightforward. We're going to condition it on x is greater than 4. We've got 5 and 6, right? So since the die is fair, each outcome in the conditional probability is likely, right? Therefore, the conditional distribution is either going to be x is equal to 5 and x is equal to 6. Okay, so we're going to have two possible outcomes because we haven't specified it to a particular value. Okay, and we're saying that has to be greater than 5 or 6. So it's obviously going to be 1/2. It's either going to be 5 or 6. And the way to write this compactly would be this way. If probability of x conditioned on x is greater than 4 is equal to 1/2, if x is equal to 5 or x is equal to 6, or it's going to be 0 otherwise. So here is, we're going to be talking about normal distribution, which is an example of a continuous one. So in a continuous distribution, the probability of an exact event occurring is 0, okay? If I said, what's the probability of x is equal to 5? It's going to be 0. Instead, you're going to have to condition on small neighborhoods of a particular value. Okay, so if I said 5, then I have to say 5 minus, say, 0.001 and 5 plus 0.001, right? So this makes conditional probability meaningful because as this epsilon approaches 0, the conditional probability will approach the conditional density. So here's an example to kind of clarify what I was just mentioning. So suppose X is a normal distribution, and we're interested in the conditional probability of Y given X is equal to X. And we know that probability of X is equal to X is equals 0 is not well defined. So we have to approximate with an epsilon neighborhood a probability of Y given X is in that epsilon neighborhood. So this captures the idea that in continuous distributions, we must think in terms of intervals, neighborhoods, not exactly point values, right? So the condition in probability theory, the conditional density is defined as fxy, the joint distribution of x and y, divided by the density of x. Okay. So here's a little bit more of a clear example. We're interested in estimating the conditional distribution of x given y is equal to 5. Okay. Given the relationship between x and y in the simulation, x is equal to 3y plus epsilon. Okay. Where epsilon is the noise term, we can infer that x is linearly dependent on y because we could see that it's a multiple, right? Specifically, when y is approximately 5, the value of x is centered around 3 times 5 plus epsilon, 15 plus epsilon. Okay. And thus, the conditional distribution probability of x given y is equal to 5 is approximately normal with a mean of 15 and the standard deviation equal to the standard deviation of the noise term, which is 1, which we see here. In the code, we're going to estimate the distribution of selecting values of x corresponding to y values within a small window around 5 plus minus epsilon. And here we simulate it. We in code, we basically compute a random normal. This is the number of simulations, 5, 1, right? Because y is equal to 5. 3 times y plus np random normal, 0, 1, n. This is the noise term. And then we build a neighborhood value around y. 5 minus epsilon, 5 plus epsilon. X given y, 5 is x mask. Okay. Its probability of x given y is equal to 5. Now we're going to be talking about conditional expectation. So we just saw conditional probability, but now we're going to be using an expectation symbol around that condition of x given y. Okay. So conditional of x given y is equal to the integral of x times f of x given y, x given y dx. Okay. And this is something that we saw earlier. It basically forms a foundation for regression and many filtering techniques in finance. So in our dice example, we see that, okay, x is greater than 3. X for X in outcomes if X is greater than 3, 1 divided by the length of conditioned outcomes, conditional expectation of X given X is greater than 3 is equal to 5. Okay. Conditional expectation can also be used in regression, and it's often called like a statistical point of view of regression. Now, if we want to predict houses using linear regression, we've got this relationship between y is equal to beta naught plus beta 1 x plus epsilon. And this is the housing price, and x would be the housing size, right? Um, in square feet. Beta 1 is the slope, the change in price per square feet. Beta 0 is the intercept, the price where x is equal to 0, and epsilon is the error term. Now, if we assume these values of beta naught is equal to 50,000 and beta 1 is equal to 200, and then the noise term is normally distributed with a mean of 0 and a variance of sigma squared, right? We could take this expected value relationship, okay, given y given x is equal to x. So like say if the housing square feet was 1,500 square feet, we could condition it on y. I mean, y conditioned on that fact. And then we could add up the values. So say 50,000 is beta naught, and then 200 is beta 1. So it'd be 50,000 plus 200 times 1,500 is equal to about 350,000, right? In real world data, obviously there'd be a random term, okay? So there could be variability in the prices. So in this example, we set it to 10,000, epsilon to 10,000, and we get 360,000. So this value represents one possible observation, right? Obviously, we're going to be working with multiple data points, right? And we're not going to just have 1,500 square feet here. It's going to be multiple. But I'm trying to show you basically one example of how it's conditioned and how you would get a particular outcome for Y based on one data point. I'm going to be talking now about law of total probability. And here we see a couple of things that's useful to know. A union operator where we take A and B and combine them, right? We see that this 3 is repetitive. So we're just going to take 1, 2, 3, 4, 5. Okay. It'll include the duplicates. Okay. 1, 2, 3. If we do the intersection 1, 2, 3, 3, 4, and 5, the only thing that these two sets share is 3. Okay. So knowing those two things, the union and the intersection, it's important to understand the law of total probability. So the law of total probability provides a way to compute the probability of an event by partitioning the sample space into mutually exclusive events, right? B1, B2, Bn that cover the whole space, okay? Formally, if B1, B2 to Bn are mutually exclusive and exhaustive events, such that the intersection of B1, say, I'll just say B1 and B2, Bi and Bj, is the empty set, okay? I and j are not equal, so I'd say 1 and 2 as an example. And then the union operator Bi is equal to the entire sample space, which makes sense, right? Because I mean, we saw these simple examples. We're going to want the entire sample space for A or B in this case. Here we're saying a union of B1, B2. If I was to expand this term out, it would be the union of B1, B2, B3, B4, B5, right? We're just adding up everything in this B, okay? So for any any event A, then we could say the probability of A given BI times the probability of BI, okay? And then we would add each of these terms from I1 to N. So if we were to expand this term out, the first one, I would say probability of A given the probability of B1 times the probability of B1 plus the probability of A given divided by, conditioned on B2 times the probability of B2. Then we condition and we expand that term out. Okay, so that's what the law of total probability is. And it's especially useful when it's difficult to compute probability of A directly, but you know how A behaves under different conditions of BI. Okay. So let's give an example of a factory example. Suppose you have a factory that has three machines, M1, M2, and M3, and it produces widgets. Now, the probability of M1 is equal to 0.3. The probability of M2 is 0.45, and the probability of M3 is 0.25. What's the probability? Like, we don't have the probabilities of what or when they're defective, right? But we do have the probabilities of when it's defective conditioned on the machine. Okay. We don't have the probability of it being defective for M1. So I don't have probability of M1 is equal to, I don't have that information, but I'm sorry, I do have that information. I don't have the probability that it's what it is for it being defective. Okay. So I have that condition, the probability that it's defective given M1. I have that information. The probability that it's defective given M2, okay? And then I could find the probability of it be a widget being defective based on these conditionals, right? So I have the probability that it's given defective given that it's M1 is 0.01. And then I have the probability of it M1 is 0.3, right? And then I could do the same thing for M2. Probability of it being defective given M2 is 0.02 times probability of it being M2, which is 0.45. And then the same thing for M3. And then I could calculate the probability of being defective, which I don't have, right? I don't have that original information, but from this information, I can get what probability of D is. And it's 0.0195 if I add it all up. Now we're going to be talking about Bayes' theorem, and Bayes' theorem actually uses the law of total probability, okay? And we see this condition formula, which we saw before. The formula is the probability of A given B is equal to the probability of B given A times probability of A divided by probability of B. So probability of A given B is the posterior, right? So it's the probability of the hypothesis A given the observed evidence B. The probability of B given A is the likelihood. The probability of A is something called the prior. And the probability of B is the marginal likelihood or evidence, right? It's the total probability of observing B under all possible hypotheses. So this would be where the law of total probability actually kicks in, okay? So like as an example, to kind of clarify the theory, what's the probability that what's the probability that it rained given that the ground is wet? Okay. So the probability of it raining, having rained, given that the grass is wet, okay, or the ground is wet, is the posterior probability. It's the probability of rain given the ground is wet, right? The probability of it's wet given it rained is the likelihood, right? The probability the ground is wet given that it rained. The probability of R is the prior, the probability it rains on any given day, and probability of wet is the evidence, the total probability that the ground is wet. Okay. So probability of being wet is the probability of wet given R plus times probability of R plus probability of wet it not being not rained given the probability of not rained. Okay. So if we're given a probability that it rained of 0.2, we can immediately calculate the probability that it didn't rain, which is going to be 0.8. And then we're given the likelihood, right? The probability of W given R is 0.9. The probability of W not given R is 0.1. So it fills in this condition. Okay, probability of W given R is 0.9. Probability of W given not R is 0.1. And then we calculate the marginal likelihood, which is the total probability. Okay, we can calculate that given those two things. Okay. And then the posterior is just basically the probability of W given R times the probability of R. Times probability of R divided by probability that it's wet. And if we do it, we get 0.69. So the total probability is important for this here, the denominator. Okay. Now we're going to be going on to independence. Two events of A and B are independent. If the probability of A and B is equal to probability of A times probability of B. Two random variables are independent if fx times fy, right? The joint distribution of xy is equal to probability of, the function fx times the function of fy. Here I give a simple example with a coin flip, right? I get the means, the probability of A and B is equal to NP mean of A and B, the intersection, probability of A times B, right? That that independence relationship. Then I also do random variables for normal. I do some kind of dependent, and I basically end up graphing it, right? So I've graphed the independent random variables for the normal, and then also for the dependent. Okay. Here's a discrete case, like I don't graph it, but here are the independent variables I do graph. And I basically want to show you the idea of, you could see the independent variables. There's no discernible pattern, right? There's no relationship. Whereas the dependent variables, you could see that there is some kind of discernible pattern. Now, if two random variables are independent, you're not going to see something like this. You're going to see something more like this. Now I'm going to be talking about application of independence in joint probability. So what's the probability of rolling a 4 on the second dice, given that on the first dice you show a 3? So people that have been following and have kind of caught on to what this idea of independent, it should be 1/6. They're both independent events, right? But we're going to go through the actual formula and use deduction to kind of arrive at a conclusion that intuitively we know as to be that the dice rolls are independent. Okay. So we see that in this conditional probability formula, again, probability of A and B divided by probability of B. Okay. A is the event we're interested in. Second dice is 4. B is the condition. The first die is 3, okay? P, A, and B is the joint probability of both events occurring. First die is 3 and second die is 4, okay? And the probability of B is the probability of condition. First die is a 3. So here's a solution. The probability of the first die rolling a 3 is obviously 1 out of 6, okay? The probability of A and B, right? Probability that the first die shows a 3 and the second die shows a 4 is, because of that independence rule, 1/6 times 1/6 is 1 out of 36. Okay. So we take that 1 out of 36 and we divide it by 1 out of 6 because we know that the probability of first die is 1 out of 6. Okay. And then when we do the math on that, we get 1 out of 6. So the conditional probability that the second die shows a 4, given that the first dice is a 3, is 1 out of 6. And this makes sense because regardless of what the first die shows, the second die will have an equal chance of showing any number from 1 to 6, so that the probability of rolling a 4 on the second die is 1 out of 6. Okay. So this was kind of the long explanation of how the idea of independence works. Okay. Obviously, you know, despite this conditional statement, we could arrive at the same conclusion just by knowing that they're independent. Now we're going to go over the ideas of covariance and correlation. Covariance is denoted by this formula, and then correlation is the covariance divided by the square root of variance x times variance y, which is basically just the standard deviations. Now, say we got this data set here, X and Y, hour studied and test score. Test score is from 0 to 5, okay? 5 being a perfect score. We could calculate the sample mean for X and Y, right? Then we take X minus X, okay? Y minus Y, okay? And then X minus X squared and Y minus Y squared. And we get 6, 10, and 6. The covariance is going to be 6 divided by 5 because there's 5 observations, right? And that would be 1.2. If I was to do it in Python, I could use this np.cov xy 10, right? You want the off diagonals in the covariance matrix here. So the diagonal is 2.5, 1.5. These would be the variances, right? And then the 1.5 here is the relationship between X and Y. Okay, so that's something important to note. And I take the correlation coefficient as well, right? 0, 1, which is still on the diagonal. Okay. So, this is something important to note. The covariances of itself is just simply the variance. Okay. Now we're going to be talking about regression and covariance. And this is a probabilistic view of looking at regression. So earlier we saw the expected value conditional and how it relates to regression. Now we're going to look at how covariance relates to regression. Okay. So linear regression models the relationship between two variables by fitting a straight line to the observed data. And the key assumption is that one variable X will be used to predict another variable Y. So you could kind of see that with a covariance, we're trying to build a relationship between these two random variables. And earlier we saw that the linear regression model is denoted by something like this, right? Beta 0 is the intercept, beta 1 is the slope, E is the error term. To estimate beta 1, now we look at how X and Y vary together, which brings us to the covariance. And we saw this, right? We saw the sample mean minus the sample mean of X, sample minus, and then yi minus sample mean of Y. So covariance of X and Y is positive. X and Y tend to increase together. If it's negative, we see that X and Y tends to decrease, okay? And if it's equal to 0, there's no relationship, right? So beta 1 is simply covariance of xy divided by variance of x. Okay, and then we've got this beta naught relationship. It's just algebra. And then we got the variance relationship. So the linear regression becomes something like this, right? And we're trying to minimize the sum of the square errors, meaning that yi minus y hat, okay? Y hat being the fitted value, okay? And then we get this goodness of fit measure, which is r squared, right? 1 minus yi, summation of yi minus y hat squared divided by summation of yi minus y hat, y bar, sample mean of y squared. Okay. If r squared is close to 1, that means it's a perfect fit. If it's close to 0, it's not a good fit. And the covariance helps to determine the direction of the relationship. The slope, beta 1 uses covariance normalized by the variance of x. And the intercept aligns the regression line with the means of x and y. And the line is chosen to minimize the prediction error, SSE. So we're always trying to minimize what line we fit versus the actual values. Okay. And here I do a Python implementation. Okay, we get the means of x and y. We get the covariances and the variances. Beta 1 is the covariance divided of x and y divided by the variance of x. Beta naught is y mean minus beta 1 times x mean. And then the predicted value is beta naught plus beta 1 times x. And we get this regression line here, the actual data. We could see that it's pretty far off. Doesn't do a good job. The distance here, right? So the distance between these lines, um, the distance between these lines here, let me show you 1 second. This would be an error here. 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 And this would be an error here. If you add up all of these errors, you get the sum of the squares of the errors, which we saw here, right? Because this fitted line is y hat, and these are the y's, right? We just expressed it algebraically, but you could also express these relationships geometrically. That's why regression is actually a pretty good learning tool. And in a later video, I'll be going over linear regression and its multiple manifestations. We've seen two. There's a lot more. Now we're going to go into joint and marginal probability, and I'm going to give you an example of a discrete case, not a continuous case here. But see, we got these data points. Device is mobile, action is purchase. So we're looking at kind of like some e-commerce store and we're looking at kind of the people visiting the site, whether it's from mobile or desktop, and seeing whether or not they're purchasing it, right? And we do this crosstab of device in action, which is a joint frequency table here. So we've got two that have purchased that are from desktop, two that have purchased, two that not have purchased that are from desktop, and two that have purchased that are from desktop, right? And vice versa for mobile. Now we calculate the probability distributions by summing over the actions for marginal device. Okay. So we sum it across here. We could sum it across device, right? To get 0.4 and 0.6. And then we could sum it across whether it was purchased or not. That's 0.5 and that's 0.5. So the marginal distribution across device and then the marginal distribution across action. So here's the last topic I'm going to be talking about. And this is the idea of convergence and distribution. So let xn be a sequence of random variables and x another random variable. Then we say that xn converges in distribution to x. Okay. And this means that the cumulative distribution function of xn converges to the CDF of x at every point of continuity of f of x. Okay, so that's f of xn, fxn as n goes to infinity is equal to fx. Okay, where f of x is continuous. I'm not talking about CDFs and PDFs. I think at a later video I will talk about that though. But so intuition, you're not saying that xn becomes equal to x. You're saying that the distribution of xn comes closer and closer to the distribution of x. Okay. So, I mean, like, you could see that, some distribution, it'll come close to I mean, it's not exact, but it'll come close as you increase the sample size. And then the central limit theorem as an example. So it's useful. Okay, I'm sorry. It's useful when approximating complicated distributions using known ones. Okay, so normal distribution. And then as a central limit theorem, the sample mean of IID random variables with mean mu and variance will converge to a standard normal where n is zero, the mean is zero, and one is the variance, standard deviation. And this means that the standard sample mean converges in distribution to a normal distribution, standard normal, which is N01. And even though the sample mean is random, its distribution shape will become more and more like a bell curve. Okay. So, I mean, you can see this is a little bit slightly skewed, but as the sample size increases, it'll become more and more like normal. Here's a central limit theorem distribution example. This is from a skewed exponential. And we take random samples from this. eventually the sampling distribution will become somewhat normal shaped. Okay. So what's the justification for this idea? The justification is that it is helpful in constructing confidence intervals, right? Because using the CLT, we know that the sampling distribution of the sample mean will be approximately normal, regardless of the original population's distribution for sufficiently large n. And we could construct confidence intervals based on this idea, right? And the z value being the critical value from the normal distribution. Okay. So this is important to know that eventually, even though we might be sampling from something that's not a normal distribution, this theory allows us to build confidence intervals around it because we know that based on the central limit theorem, that as the sample size increases, we could treat that non-normal sample to something that's normal. And in hypothesis testing, we could see that we could make inferences about the population mean, okay, based on like something like the z-test, right? For the f-test, we replace the population standard deviation with the sample standard deviation, which is s divided by square root of n. And both of these tests assume that the sampling distribution of the sample mean is approximately normal, which is guaranteed by the central limit theorem. Okay. Estimating the sample mean, the population mean, the sample mean x bar is an unbiased estimator of the population mean, meaning that x bar will equal the mean. Okay. When the size grows. Okay. So additionally, the variability of x bar is known as to be calculated by the standard error is equal to sigma divided by the square root of n. And because of the CLT, we know that as we draw more samples, this distribution of x bar will converge to the population mean. Okay. And we can estimate mu using x bar with a known degree of uncertainty, which is a standard error. So without the CLT, we wouldn't be able to run these tests because we have to, the theory kind of dictates us to use something that's normal, a normal distribution. And the central limit theorem bridges, okay, the idea that even with a non-normal population, we could make inferences based on the idea that as the sample size grows, it will eventually approach normal. So here's a basic summary table, the confidence interval, why CLT helps. It allows us to assume that X bar is normal to compute the ranges. ZT test justifies using the normal or T distribution for X bar. And then estimating mu tells us that X bar converges to mu eventually under the CLT, and its variability is known. So that basically sums it up for this tutorial. Hopefully what you've taken away from this is that these are highly useful ideas, and it could be leveraged in multiple disciplines, including quantitative finance and machine learning. Hope you enjoyed it. Thank you very much, and I will see you soon.